So we are looking at the actual math of confidence intervals today. And we are gonna look, what's called a one sample Z confidence interval for a population proportion. So here are the following conditions that must be met. First, P hat is the sample proportion from a random sample. And then the sample size N is sufficiently large. So notice right here, we don't know what P is. That's what we're trying to estimate with the confidence interval. Therefore, we have N times P hat is greater than or equal to 10. N times 1 minus P hat is greater than or equal to 10. Okay, so this is large counts. And then we have the 10% condition. The sample size is small relative to the population size. So the population must be greater than 10 times the sample size. Okay, so basically three things. It's got to be a random sample. We got to have the large counts, which for proportion is N times P hat greater than or equal to 10. N times 1 minus that. And then we have the 10% rule. Here's kind of the structure for a confidence interval. For proportion, we have P hat plus or minus Z critical value. Then we have the square root P hat times 1 minus P hat divided by N. Remember, this Z critical value is what we looked at in the previous notes. Okay, where we're calculating based on the confidence interval. Okay, and this right here, this part right here is known as the standard error. All right, we have to do the assumptions conditions because we have to know that the sample size is large so that the sampling distribution is approximately normal so that we can use the standardized Z-score, the Z-score. When the standard deviation of a statistic is estimated from the data, the result is called the standard error of the statistic. So we're going to look at an example. We have a little mnemonic device that I want you to remember. It's called PANIC. Okay, which is what we use for confidence intervals. PANIC stands for parameter, assumptions or conditions, name of the test, the actual interval, which is the math portion, and conclusion. So this says a recent study investigated the effects of a buckle up your toddler's campaign to get parents to use the grocery cart seatbelt. Investigators observed that 192 out of 594 parents buckling up their toddlers. Assume it is reasonable to regard this sample as representative of the population of parents with toddlers. And it says construct and interpret a 95% confidence interval for P, which is the true proportion of all parents who buckle up their toddlers. All right, so here we go. Parameter. We need to define the parameter. They did that for us in the stem of the problem, but I'm going to go ahead and rewrite it. So I have P is okay, so we want to define this. P is the true proportion of all parents who buckle up their toddlers. Okay, also in this section, in the first section, you need to write down a couple of things because we will use them later. So we know that the sample size is 594. And then I'm going to find P hat. So it says 192 out of 594. So I got 192 divided by 594. So take your calculator and find that proportion. And I got 0.323. Okay, next we have the assumptions, which we looked at above there. Okay, so you need to write these down. We are going to assume a random sample of shopping parents and toddlers. And it doesn't really say that in the stem of the problem, but it probably should, all right? Normally, they will tell you, okay, an SRS was taken or something like that, right? But we have to have that, otherwise we have biased data. Okay, number two, population. Let's do the 10%. So the population of parents of toddlers must be greater than my sample size, 10 times my sample size, so 10 times 594. And this is reasonable. And then we got to check the large counts. And you need to write these out like I'm doing. So this is n times p hat is greater than or equal to 10. N times 1 minus p hat is greater than or equal to 10. Okay, so my sample, and like this line right here, as I just wrote it, is not enough for credit. I need to plug in the numbers. So I've got 594 times p hat, which was 0.323, greater than or equal to 10. And we found that was 192. And so that works. And then over here, we've got 594 times 1 minus 323 must be greater than or equal to 10. Let's see, 594 minus 192, that's 402. It's obviously greater than 10 also. Okay, so I list all my assumptions, check that they are met. And then the N stands for the name of the test. So what is my level? Look at the stem of the problem again. Level is. What did they ask me to find? Okay, so this is a 95% confidence interval. Okay, and so I'm gonna say for a one sample proportion. And so this is a one proportion Z test. So when you are working these problems, there's a bunch of different confidence intervals that we're going to look at, but you need to kind of put them in categories. All right, is it one sample or two sample? Is it a means or a proportion? Okay, and so based on that, there's a certain procedure that you follow, certain conditions that must be met, certain formulas, all of that. Okay, but this comes from one sample and it's a proportion. Therefore, this is a 95% confidence interval for a one sample proportion. So the interval is where we actually set up the math and calculate the interval. Okay, and so my advice is to write down the math and then use your calculator to calculate it. It will do that for you. All right, the actual math on this one is not really that complicated, but they can get complicated, and so it's it's easier a lot of times to set it up and then use your calculator. Okay, so here's the formula. We got p hat plus or minus. What goes next? Z critical value. And then we've got square root of p hat times 1 minus p hat divided by n. And let's plug those in. So p hat was 0.323 plus or minus. Okay, so p hat is serving as the point estimate. Z critical value of a 95% confidence interval. I said it might be helpful to memorize that, but anybody? It is 1.96. And we get that, okay, it comes from, I've got 95% in the middle, then there's 2.5% here and 2.5% here. So if I want this right here, that's where my Z critical value is. I get all of the area to the left. So that's going to be inverse norm of 0.975, which is 1.96. That's where that comes from. Okay, so I've got this, then I've got square root 0.323, 1 minus 0.323 divided by the sample size, which was 594. So what your calculator is going to do, it's going to take this, it's going to add the 1.96 times the square root of all of that, and then subtract it from 0.323. Okay, so let me show you that on your calculator. So go to the Scratchpad. And we go to menu. And then statistics. And then we are going to go down to option 6, which is confidence intervals. And then you will see several different types of confidence intervals. And this was a what? The one sample, proportion, Z interval. Proportion, okay, proportions are always Z intervals. Okay, so I'm going to choose option number 5, one prop Z interval. And then fill in the data there. So number of successes, it was 192, I believe. Is that right? Let me make sure. Yes. So 192. The sample size was 594. And then my confidence level, the default level is like 95%. So I'm going to leave that, but if it's not, I will need to change that. And I'm going to hit OK. And so look, it gives you p hat, it gives you margin of error, it gives you sample size. And then what we're looking for here is the upper and lower bounds of the interval. So the lower bound is 0.286, the upper bound is 0.361 there. All right, so let me go back to the notes there. And fill that in. All right, so this gives me an interval from 0.286 to 0.361. And the last thing I'm going to do is write my conclusion, which is the interpretation of the interval. We say I am 95% confident that the true proportion Parents that buckle up. Parents that buckle up their toddlers in grocery carts. Is between. 0.286 and 0.361. Any questions for me there? We're gonna do like one more confidence interval and then one last problem. So let's go ahead and do this. It says Mrs. Quinn's class took an SRS of 102 pennies and discovered that 57 of the pennies were more than 10 years old. Calculate and interpret a 99% confidence interval for P equals the true proportion of pennies from the collection that are more than 10 years old. All right, so here we go. Got a panic. The parameters, it gave it to me in the stem of the problem, but I'm gonna go ahead and define it. P is the true proportion of pennies from the collection that are more than 10 years old. Also, in the parameter section, I'm gonna write down my sample size. N is 102. And so P hat, 57 of them were more than 10 years old. So I got 57 out of 102. And that gives me a P hat of 0.559. Next up, A. We do the assumptions without looking. First assumption. Random sample, okay. So random sample pennies. This is true because it says that it came from an SRS. Okay. Next, 10%. So population of pennies greater than 10 times 102. And this is also true. And then we got n times p hat greater than or equal to 10. N times p hat. Excuse me, it's n times 1 minus p hat. Must also be greater than or equal to 10. And I'm going to fill in those numbers. So I've got 102 times 0.559 greater than or equal to 10. And it was 57. So yes, that works. And then 102 minus 57, that's going to give me 45. So 102, 1 minus 0.559. This also will be greater than or equal to 10. And it is. Okay, random sample, population of pennies greater than 10 times the sample. And then this is the large counts. Right, the N is the name. So what's the name? What's my level? 90 what?
Or 99%.
99% confidence interval. For how many samples were there? One. Proportion or means, proportion. So this is a 99% confidence interval for a one sample proportion. Okay, PANI is the interval. It's p hat plus or minus z critical value square root p hat 1 minus p hat divided by n. So p hat was 0.559 plus or minus. What is my z critical value for a 99% interval? Okay, 2.576. And if you did not remember that, I could get that from inverse norm 0.995 0.1 gives me that. Then I've got square roots of 0.559 1 minus 0.559 divided by 102. So take your calculator and calculate the confidence interval there. And someone want to help me out there? Interval, it's the lower bound. What was the upper bound?
685.
0.685. Something like that. Okay. That's what I got. So my conclusion, I am 99% confident that the true proportion of pennies greater than 10 years old is between 0.432 and 0.685. And the last part here says, is it plausible that exactly 60% of the pennies in the collection are more than 10 years old? Explain. And the answer to that is yes. Okay, why do I say yes? What does the interval give? Gives a percentage of what? All right, it gives me a range. It gives me an interval of plausible values. Okay, so is 60%, is 0.6 within the interval? Yes, therefore it is a plausible value. Okay, so we're gonna say yes. Because 0.6 is included in the interval. It is plausible that 60% of the pennies in the collection or greater than 10 years. Okay, one thing also that I noticed on some of the quizzes that we need to correct going forward. You should never say that something is false or true. The way the language, we haven't really gone over this, and so I didn't count off on it on the quiz. Provided that you gave certain information, okay? But you should always say there is convincing evidence that, and then put it in context, or say there is not convincing evidence. So like this, is it plausible that exactly 60% of the pennies in the collection are more than 10 years old? Well, yes, because 0.6 is included in the interval, right? But the language, which we will get to later, is important. Okay, so we say, yes, it is plausible because, okay, or there is convincing evidence because, or there's not convincing evidence. Okay. All right, well, let's take a short little break. Okay, so here we go. Last thing. This actually has a lot of practical applications. To determine the sample size that will yield a certain confidence interval for a population proportion P with a maximum margin of error, solve the following inequality for N. Okay, so we've got Z critical value times square root of P hat times 1 minus P hat over N must be less than or equal to the margin of error. Where P hat is a guess value for the sample proportion, the margin of error will always be less than or equal to if you use P hat is equal to 0.5 here. So let's look at this example. It says, suppose that you want to estimate P equals the true proportion of students at your school who have a tattoo with 95% confidence and a margin of error of no more than 0.1. So determine how many students should be surveyed to estimate P within 0.1 with 95% confidence, okay? And so this is helpful when we're trying to decide how many people we need to survey, for example. So I'm going to say, so there's kind of two different scenarios. They give you a P hat, or if they don't give you a P hat, then you should use P hat equal to 0.5. And so I'm going to say, because we don't have any previous knowledge about the proportion of students with a tattoo, we will use P hat equal to 0.5 to estimate the sample size. So they give us a P hat, we use that. They do not give us a P hat, then we're going to use 0.5. So here's my formula. We've got Z critical value square root P hat 1 minus P hat divided by N. This must be less than or equal to margin of error. So my Z critical value, what's my confidence level? 95, therefore Z critical value is 1.96. And I've got the square root. The square root. Where did that come from? P hat is 0.5. So 1 minus that is also going to be 0.5. And the sample size is what I'm looking for. And then this is gonna be less than or equal to, they wanted a margin of error of 0.1. All right, so I'm gonna do a little algebra. Oh no. So I'm gonna solve for n. So I'm going to multiply by the square root on both sides. That will get rid of that. Okay, so that's gonna give me 1.96 times the square root of 0.25 less than or equal to 0.10 square root of n. So now I'm gonna divide, I need to solve for n, so I'm gonna divide by 0.1 on both sides. So now, to get rid of the radical, I'm gonna square everything. All right, and so that's gonna give me n. And over here, I'm gonna have that. So take your calculators. And we put in 1.96 times the square root of 0.25 divided by 0.1, and all of that is squared. Okay. That's what I got, right? And this is important, okay? Because what are we sampling? What are we sampling? People, students, right? So I've got to have at least 96.04, and that 0.04 matters, okay? Because if I just use 96, it's not gonna work out the math. So since I'm dealing with students, I have to round that up to the next whole number. So we need to survey at least 97 students to estimate the true proportion of students with a tattoo. With 95% confidence. And margin of error of 10%.